Today we'll be evaluating the performance of calorimeter clustering algorithms. My name is Alexandra Ballo, and I work with Brian, Isabel, and Alina Lazar from Youngstown State University on this project. Scientists at CERN are recreating mini Big Bangs and observing these collisions with silicon detectors. Event rates have been speeding up, and resolution of detectors are improving. In fact, the data is projected to progressively increase by 10 times before the year 2025. With scientists already sifting through petabytes of data per year, 10 times that simply cannot be pre-processed real-time. In order to solve the solution, particle physicists are working with machine learning specialists in a Kaggle competition titled TrackML. In TrackML, the machine learning specialists are given dots where particles pass through the detectors shown in green in the picture to the right, and are supposed to create the trajectory the particle took through those dots. The quickest method to group together individual unlabeled impact points from the same particle trajectory is clustering algorithms. We look to expand preliminary clustering results from the current literature to include a deeper analysis of different clustering techniques. Algorithms such as DBSCAN and sparse binning were looked at before but not compared directly. The optimized Python clustering algorithm to group similar impacts and find particle trajectories developed here can be used by the scientists at CERN to quickly determine the results of their experiments from the Hadron Collider. The Kaggle competition provided many different types of data for the competitors to use. The training dataset they included provided the recorded hits, their ground truth counterpart, their association to particles, and the initial parameters of those particles. While the test dataset only includes the recorded hits, the training dataset had 8,850 events split into 5 files. There was also a sample available to use which had the first 100 events from the training dataset. The detector used to record this data is built from silicon slabs arranged into cylinders and disks, which measure the position of the particles that cross them. The trajectory of a particle present in a hadron collider forms a helix because of the magnetic forces present in this type of environment. So to determine the trajectory of a particle, the impacts need to be matched with the helix that contains the most of these impacts. Following the lead of several of the challenge contestants, we start by assuming there is a small cylinder about the origin which the helix is contained in. Then using the initial parameters given in the training data and creating a variable to help determine whether the helix is clockwise or counterclockwise, we can increment the values of the different variables in the helix equation through all possible combinations to determine which of these helix best fits the hits. The first clustering algorithm we'll be looking at is called DBSCAN, or Density-Based Spatial Clustering of Applications with Noise, and it takes a parameter that sets a minimum number of data points. Then it checks each data point in the dataset and finds all other points within some epsilon distance of that point. If there is more than the user-defined minimum in the epsilon neighborhood, then these points form a core. Otherwise, this data point is considered noise. The cores are then recursively merged into clusters. This density-based approach often enables DBSCAN to find nonlinear clusters better than other algorithms. The other clustering algorithm we will look at is sparse binning. Binning assumes that each feature is within some interval for all hits. Each feature is then given a bin number. If all bin numbers for every feature is the same between 2 points, those 2 points are then clustered together. To score the clustering methods described, we'll use the scoring system developed from the Kaggle competition. We ran the same 3 events with DBSCAN and sparse binning, and those are listed in the table. As you can see, DBSCAN scored better. However, DBSCAN took 3 days for those 3 runs, while sparse binning we were able to run 11 runs in only 1 day. Sparse binning averaged 0.74 in those 11 runs. So overall, DBSCAN is more accurate, but it requires so much more computational time to run that sparse binning is also a valuable tool. These are the resources we used to compile this research. Thank you for listening.